Lesson 2. Ben, what's the title? Lesson 2 what? Impulse. My mom says I have impulse, Ben. She means something different. Impulse is actually a physics term. Don't write this next bit down. Look up. I'm going to write it out in English, and then we're going to abbreviate. Impulse is change in momentum. Those are equivalent terms. Don't write that down. If you see the phrase change in momentum, you can also say that's the same as a word that starts with letter I. If you see the word impulse, you can think that's actually the change in momentum. The change in momentum. Oh, got somebody just coming back. Got to interrupt my lesson. This is why I don't like. Why did I say not to write that down? Well, first of all, we have an abbrev for the word momentum. What letter or symbol are we using for momentum? P. We also have an abbrev for change in. In fact, I think it's the very, very first thing I put on the front of your formula sheet. What's our abbrev for change in? What symbol can we use? It's not a triangle. It's in math. What do we call it when we want to nerd out in physics? What? Delta. Okay. So if you see the phrase impulse, you can think that's the same as change in momentum. That's what it is. Oh, and Liam, from the front of your formula sheet, the very first thing, what's change in anything? Something minus something. Say it again, you're right. I have an abbrev for final. What can I write instead of the word final? What did we do for velocities? What did I use? Okay, what did I use? You did good on this test. Yes, and? Yeah. That's you're going to memorize in physics 12, because in physics 12 I ask for change ins. What's the change in voltage? My kids all know, find the final voltage minus find the initial voltage. Hey, what's the change in energy? They'll find the final voltage minus the initial voltage. What's the change in kinetic energy? Final kinetic energy minus the initial kinetic energy. My kids all know in physics 12, I'll say to them, what's change in anything? And they'll all say back, final minus initial. So just for the giggles, what's changing anything? Everybody. What's changing anything? Everybody. Final minus initial. By the way, it's almost a tongue twister. I already heard somebody do finus minus. Don't feel bad. It happens to everybody. But change in anything is final minus initial. Change in momentum as a special word that starts letter I. Impulse. Okay. It says prove that change in momentum, impulse, equals mass times change in velocity. We're going to do a proof. Don't panic. Change in momentum looks like this. Equals mass times velocity change. That would be m delta v. But above the equal sign, I'm going to put a question mark because I'm trying to prove that they're equal, Aiden. I don't know that they're equal, so are they equal? That's my abbrev for that. To prove one thing equals another thing, what you're going to do is you're going to try and turn one thing into the other thing. And I'm going to just work on the left-hand side. Jaden, that delta P, which is change in momentum. Jaden, what's change in anything? What's the F and the I in abbrev for? So I'm going to argue that I can write this as P final minus P initial. And I'll just drop the m delta v down. I haven't proved it yet, so I'll still put a question mark there. But you okay with that? That's what change in means. Ooh, Jaden, from your formula sheet, how do you calculate momentum? What's P equal to? Good, loud and proud. What? So what would P final be? mv. And what would P initial be? mv. So I can write this next line as mv initial, final minus mv initial. Does that equal m delta v? When I got to this line this morning, I had one of my students say, yeah, it does. It does, but we need to do a little more to make them identical. I'm going to pull out the GCF trick again. On the left-hand side, is there an M in both terms? I'm going to factor out an M. I'm running out of room, so I'm going to move over to here, and I'm going to write this as M bracket V final minus V initial. Does that equal M delta V? Well, what's final minus initial the same as? What? Change in. In other words, I think I can write this as M change in V, which is the same as M change in V. I was able to make the left side look like the right-hand side. So what does that mean? It means one way to find impulse is, don't write this next bit down, M delta V. Although I don't usually write it that way. Tori, what's changing anything? I usually write it as M V final minus M V initial. You don't need to write that one down just yet. We'll put it in somewhere else, and I kind of snuck it in already. Okay. Oh, and what's impulse defined as? What did we say it was? Change in. I'll write it in English just this once, but from now on, I'm going to write delta P because it's less writing, and you know I like to abbreviate. So one way to find impulse, one way to find change in momentum is to go mass times final velocity minus mass times initial velocity. How do I know I'm going to use that? If they give me a final velocity and if they give me an initial velocity and a mass, which sounds kind of Captain Obvious, Liam, but don't overcomplicate it. If they give you a mass and a V final and a V initial and they say find the impulse, you can do that. But there's another way to find impulse. We're going to generate an impulse equation. Example 1 says, fill in the steps below to find the impulse equation. Take Newton's second, F equals ma, and get the a by itself. I think I named that after Sophia, did I not? Get the a by itself. F over m. And then from way before Christmas, we have VF equals VI plus AT. Yes? Get the A by itself. Put a dot above the A. What would drop down like a domino? Good. Then what? Minus the VI. Then what? Divide the T. Right? Ben, here's my question. Does this equal A? Say yes. Does this equal A? Then they equal each other. Yes? So we're going to let these two expressions equal each other. I'm going to go F over M equals VF minus VI all over T. And you'll notice I'm putting vector symbols above the stuff that's vectors because direction is going to become important again during this unit, during this lesson, in fact. Except I have one fraction equals one fraction. I'm going to cross multiply to get rid of the fractions. Dividing by m on the left is the same as timesing by m on the right. Dividing by t on the right is the same as timesing by t on the left. I'm going to write it, next page, as f delta t equals m, and then in brackets, v final minus v initial. Why did I put a delta in front of the time? Time has always been a change in. We got a little sloppy and stopped writing it, but because this is a change in on the right, I put the change in here. And then, Luke, what does it say? Substitute what? Oh, what's m times VF minus VI the same as? Yep. Okay. I can say this. Force times the change in time is one way to write impulse, but another way to write impulse is m change in velocity. Can you find that one on your formula sheet? I think I gave you that on your formula sheet, but we're going to add to it a little bit. It should be, I think, right next to momentum, although I might have written it in a different order. Oh, you got your sheet here. Good. I can read upside down. Yeah, I did the delta P first, and then the M delta V, and then the F delta T. Carson, can you point to it? Yeah, but halfway down in the middle. Right there. Okay. This is actually three equations in one. You have a bit of room underneath. Hang on, show me. Or above or to the right of it. Here's what this really means. Sometimes you can find impulse, change in momentum, by going force times time. That's one version. Or sometimes you can find the change in momentum by going mv final minus mv initial. It's a terrible vector sign. Or sometimes you can say force times change in time equals mv final minus mv initial. If you want to, you can write those three versions right next to the impulse equation, but you might not need to, because that's what that line is saying. It's saying each of those can equal each other, mix and match to your heart's content. It's technically got three little equations baked inside of it. How do I know which versions of this to use? Depends on what they give you. We'll figure that out in just a second. But here's what it's really saying, Ben. If you have a force acting for a time, it'll change an object's momentum. Well, of course it will, because F equals what? If you have an unbalanced force, an object will accelerate. And if it's going to accelerate, it's going to change its momentum because its velocity is changing. F equals what? I fibbed to you when I said that was Newton's second law. Newton was not that interested, Liam, in acceleration. He was way more interested in impulse. He actually didn't write F equals ma. He wrote F equals impulse over time. That's how he wrote his version. But that can be turned into F equals ma, which we usually start with just to get you into the shallow end of the pool. So what this equation signifies is that a force acting for a time will change the amount of momentum, will change the momentum of a system. So we have three equations baked into one. Force times the time, delta t, is going to be mass times the change in velocity, is going to be the change in momentum. Usually that one I write as mv final minus mv initial, because it's easier to get a vi or a vf by itself when it's not inside brackets. You'll see what I mean in the next couple lessons. Question, Elijah, have we seen F force before? Yeah. Have we seen time before? Yeah. Have we seen mass before? Have we seen VF before? Have we seen VI before? So I'm going to argue none of this is really new. In fact, this equation here is redundant. You can survive just fine without it. What it is a really nice shortcut. Jaden, I'll show you over the next couple of days. It can save you about 4 lines of writing, which I'll take. I wrote here, you may have noticed that we seem to be paying more attention to vector notation than we have been for the past few lessons. This is because in momentum problems, there are often changes in direction, and so we need to use very careful vector analysis. Let one way be positive and one way be to make sure we get the correct answer. Okay? Example 1. Let's jump on in. Now, you've all just turned the page. You should have the impulse equation on your green sheet where you can see it. I'm going to write it here. It was impulse equals mv final minus mv initial equals force delta time. Okay. Mateo, we're going to jump on in. It says this. A baseball is pitched horizontally due east at 38 meters per second. After it's hit by a bat, it moves horizontally due west at 55 meters per second. Mateo, what word is this right here? What word is this right here? Did they give me directions in this question? Say yes. Yeah. Are there different directions? In other words, is everything east, 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 east? Okay. You know what that means? I'm going to have to let one way be positive and one way be. Yeah. I've used this phrase with you before, but I'm going to revive it. I'm going to be lazy but organized. Okay? This is the minimum amount of writing for the maximum organization. You're going to decide, Mateo, east, do you want it to be positive or negative? I don't care, pick. Okay, so because you decided to make east negative, everybody put a negative in front of the word east and in front of the 38. What's west then? Put a plus sign in front of the W and a plus sign in front of the 55. Now, as long as we're consistent then, if we get a negative answer, what direction will we call that? If we get a positive answer, what direction will we call that? West. And by the way, it doesn't matter which way you pick as long as you're consistent. My morning class made east positive and west negative. It'll be okay. All right. What's A asking me to find, Mateo? Impulse. Impulse is change in momentum. The question is, which version of this equation am I going to use to solve this? One version says force times time. Do you see a force in newtons or a time in seconds in this question? Do you see a force in newtons or a time in seconds in this question? Hey, no. What? No. Okay. So I'm not going to use this version. It's also mv final minus mv initial. Did they give you a mass in this question? Did they give you a final velocity? And an initial velocity? Ding, 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 ding. I'm going to use this version. That's how I figure it out. I look at what they gave me. So we're going to go mv final minus mv initial. What was m? I've scrolled down. What was m? I scrolled down. M. It's mass. Yes, you're overcomplicating it. What? Yes. Good. What was VF? There's a minus sign. M.144. What was VI? Careful. Careful. What? Okay. Time to go to your calculators. What do you get for the impulse? Aiden, what'd you get? Yes, time to go to your calculators means time to go to your calculators. I think it's 13 something, but I didn't do that in my head. I'm going from memory. 13.4. Is it, I think it's 392. Yeah, is that right? So I'm going to go positive or negative, first of all. So positive 13.392. So now let's write 13.4 units. Well, let's see. Mass, units for mass, everybody. Velocity. So the units, kilogram, meters per second. Direction, if we got a positive answer. What did you let be positive? At symbol to show it's a direction. West. You can abbreviate west with a W. Capital W, sorry. Okay. B asks, all right, where did this impulse come from? Don't overcomplicate this. What gives a baseball its change in momentum? 3 letters, starts with a B. Someone said it. Yeah. Okay. Owen, what's C want me to find? What does it want me to find? The what? Yeah, average, because I suspect it's a changing. I'm just hedging my bets. It wants me to find the force. Put your pencils down, look up for a second. Okay. I will give you full marks if you go F equals what? Don't write this down. Do you know M? Do you know A? Colonel. But I can find A. I can go A equals VF minus VI over T. Do I know VF? Do I know VI? Did they give me time in part C? And I have no problem if you do that. I will give you full credit. It's about 3 or 4 lines. You'll get the same answer. But what did we find in part A? We did not. There was a word in front of it. Ah, that's important. We found the impulse. There is a version of impulse that has a force in it. Write this down. And then, Owen, if you'd be so kind as to get the F by itself. Ben, write this down. How'd you get the F by itself? How would you move the... Yeah. Do I know the impulse? Yeah, Mateo found it. Did they give me the time? Yeah. This is nice, 1 line and we're done, as opposed to 3 lines. The impulse equation, one of its uses, it's a lovely shortcut because it contains within it forces and V finals and VFs and T's. What was the impulse? It was 13.392. Ooh, what's the time, Owen? What does it say? How much time did this take? What's a lowercase m? Not micro. Go check your formula sheet and then tell me the 10 to the. It's milli, which is 10 to the, is it -3? Okay. You probably still have the 13.92 sitting as your answer button. So go answer button divided by, you'll probably need to put brackets around the bottom because more than one thing on the bottom. Use your scientific notation button. Oh, 13 point, oh, sorry, it was 13.392, right? I said 13.92 out loud. 13.392 divided by bracket 8, no, 0.8, and milli is 10 to the -3. I got 16,740. Sahib's nodding. Owens, that what you got too? Did you go 0.8? Because I think it's 0.8. milliseconds, which is pretty fast. 16,740 newtons. Did we get a positive answer or a negative answer? Be stupid obvious, Owen. So if they ask for a direction, west. Okay. This morning class that let west be negative, we got a negative answer because our impulse was also negative, and so we had a negative divided by a positive, which is a negative. Long as you're consistent, you'll end up with the same direction that we do. It just may be that yours has a negative because you decided to let that direction be negative, but then you'll interpret the same way as we do. Give me 1 second here. Let me pause the video lesson. Somebody at the door. Okay. So that, again, Tori, I have to emphasize, you could have gone F equals what, and then said, oh, A equals VF minus VL over T, which all of you were pretty good at. But that's 3 lines, 1 line. What's D asking me to find? Okay. I could go, don't write this down. But what did I just find in part C, Tori? What did I just find? No, part C. What did I just find? Keep reading. Part C. What did I just find? Oh, is there a version of force that has an acceleration in it? Yes, there is. Sophia's theorem. You back with me now, kiddo? We can just do this. It's going to be your answer button divided by, I've scrolled down. What was the mass? Should be a pretty big acceleration because, yeah, baseball accelerates when it gets hit by a baseball bat pretty fast. I get 116250. I'm going to just round to 3 sig figs, Jaden, if that's okay. That's an acceleration, so it's meters per second squared. Positive answer, it's accelerating to the west if they needed a direction. Just to let you know, I could have gone VF, which was 55, minus VI, which was negative 38, divided by T, which was 0.8 milliseconds. And lo and behold, I get exactly the same answer. Either of those approaches are fine. I'm just trying to pick the laziest one to get there because lazy but organized. Example 2. I said to you the other day that momentum and impulse are our best tools for analyzing collisions. A tackle is a collision. So if any of you are football players, 2A says, what's the momentum of a 112 kilogram football player running due north with a speed of 3.6 meters per second? Ben, what's 2A asking me to find? Yeah, does it say the change in momentum or just momentum? What's our equation for momentum from your formula sheet? What letter are we using for momentum as our abbrev? Who remembers? Nope, that's change in. Sorry? P? So find the equation for momentum on your formula sheet. Yeah. I'll give you a hint. It says P equals, because that's what you said. Yep. And not delta. This is not change in, just that. Okay. What's the mass? What's the velocity? How much momentum does this person have? Let me know what you get. Now, I notice you said the 3.6 was positive. What direction are we going in this question? So you've let north be positive. So a positive answer means north. What if we ever get a negative answer? That would be, okay. So let's go 403.2 units. Yes! I knew I could count on you. Well done. And if they wanted a direction, I could say north. Okay. Anybody here play football? Okay. Anybody here play hockey? Ice hockey in particular? Okay, so this is also the physics of a body check. What if the person was heavier? Would they have more momentum or less momentum? Be stupid obvious. More means to bring someone who's heavier to a stop, you to hit them harder. What if they were going faster at the same weight? Would they have more momentum or less momentum? Again, be stupid obvious. If they're going faster, more. So you can increase your momentum by being bigger or by being faster. If you're both, you're one of those athletic freaks that nobody can bring down. They're out there, not many, but they're out there. What? Ooh, Liam, what's B asking me to find? Impulse, which is change in momentum. I'll write that down. Must a tackler impart to the football player to bring him to a stop? Now, the impulse equation on your green sheet, that's that 3-in-1 equation. Am I going to use force times time? Do you see a force in newtons or a time in seconds anywhere in what they've given me so far? No. You know what? I think I'm actually going to use the definition of change in. What's change in anything? Something minus something. I think it's going to be the final momentum minus the initial momentum. Now, how did I know to do that? Because in part A, we found the initial momentum. Stop. What's the final momentum if you're stopped as a number exactly? So it's going to be final momentum minus initial momentum. You probably don't even need a calculator to go 0 minus 403.2 in your head. The answer is going to be negative what? Kilogram meters per second. Ben, what direction is this? Negative. Yes. And again, this is kind of Captain Obvious, but at south while you're writing that down. Yeah, if someone's running north and I want to bring them to a stop, I have to be moving south to do that. If I want to bring them to a complete stop, I have to have exactly the same momentum as them to cancel theirs out. If I have more momentum, I'll drive them backwards. If I don't have enough momentum, they'll run through me and pull me along. There's the physics of tackling. There's the physics of tackling. Okay. Ooh, Matt, what's part C asking me to find? Force. I could go F equals what? But what did I just find in part B? Impulse. I'm going to use the force version of the impulse equation, the one that says impulse also equals force times change in time. Get the F by itself. F is going to be the impulse divided by the change in time. It's going to be negative 403.2 divided by 0.8. Even? Units, it's a force. Did you get 504 or did you get negative 504? So, Ben, what direction must this force be applied if it's negative? Yeah. Okay. Matt, how long did it take us to bring this person to a stop? How many seconds? They told me. 0.8. What if I want to bring, because that's a fairly long time. That meant this person continued to gain yards. What if I want to bring this person to a stop quicker? If this number gets smaller, what's going to happen to this answer? Because I still got to get rid of all their momentum. Yeah. And again, it's kind of Captain Obvious, but if I want to bring you to a stop faster, I have to hit you harder. There's the physics of why, the proof of that. And the harder I hit you, the less time required to bring you to a stop. The weaker I hit you, the more time it's going to be. You'll drag me for a while as I bring you to a stop. Oh, and if I'm not canceling out your direction, sorry? Sorry, test it? Play football. Jaden, although we solved this using impulse, we could have solved this whole question using F equals MA and VF equals VI plus AT, get the A by itself. So why did I bother doing this impulse thing? Well, the main reason is it's our best tool for analyzing collision problems, which is going to be next lesson. But there are some questions that can be best answered with impulse. Turn the page or next page over. I'm not going to do the experiment because I don't want to break eggs and waste them, but we're going to use our imagination. If I have two identical mass eggs and I raise them to the same height and I drop one on cement and one in a pail of water, how come the one that lands in the pail of water survives? And how come the one that lands on the cement breaks? Yeah. You're on the right track, but I think you're wrong because I think both of them hit at exactly the same velocity, one hitting water, one hitting cement. And I think they have the same amount of velocity to get rid of, same amount of momentum. What? What does that change as a physics variable? Okay. Both have the same impulse because we want their final to be 0 and their initial would be the same speed right when they hit the ground because they got dropped from the same height. You okay with that? Draw a little line down the middle here. I'm going to write floor, H2O, water. What does the water do to make the egg survive in terms of impulse? What's the difference between landing on cement and landing in water? Which variable changes dramatically? Time. One way to think about this, impulse is force times time. So both have the same impulse. They both have the same force delta T. On the floor, the delta T is really small. You need a big force. Is that okay if I write it like that? A huge letter and a tiny letter? With the water, time is really big, small force, to get the same impulse. And we've just explained the physics of most of our car crash safety measures. We build in crumple zones to lengthen time. Airbags lengthen the time of collision. Seatbelts lengthen the time of collision. Those big barrels of water, those plastic barrels that you see in front of cement barriers, we're all about, can we increase the time of collision because that makes the force smaller. And then you were correct because F equals what? Does your mass change during a collision? So if time changes and force gets smaller, acceleration gets smaller. And I think I've told you, and you're hearing me repeat myself, what does damage in a car crash is acceleration. Not velocity, not force, it's acceleration. That's what does damage. So if you can make acceleration smaller, we're good. It says Mr. Dueck needs to pummel someone, but only for the sake of good physics. Ah, yes, I do. So damage from change in momentum isn't caused by how much momentum is absorbed, it's how fast the impulse occurs. All of you have gone from 100 kilometers to 0. When? Every time you leave the freeway. You go on an off ramp, that takes some time. Then you slow down a bit more, That takes some time. Then you get on a city road at 60 kilometers per hour, slowing down some more. Then you turn into your subdivision. Now you're at 40 kilometers per hour, slowing down some more. Then you turn into your drive. You spread it out over so much time, you don't even notice that you've gone from 100 kilometers per hour to zero. It's not something you even brace yourself or think about. Now, if you went from 100 kilometers per hour to zero in 1 second, that's going to get your attention. It's all about increasing time. So where has this occurred? Leaving the freeway slowly, right? As you drive home. This doesn't just have some implications in car safety, also has some sports implications. Here's another way, example 4, to think about the egg question. Why do they use bales of hay to line some racetracks? Well, the advantage is being brought to a stop by a bale of hay. You still have the same mass times velocity impulse to get rid of. Bigger time, smaller force, smaller time, bigger force. Pitt Meadows tragically experienced this about 16 years ago. We had a race car driver named Greg Moore. There's a few buildings named after him. He was a ranked Formula One race car driver, and I'm not going to say go look at the video, you don't want to, but he hit a wall, was dead instantly. And they've redone that wall, and they put a cushion in on that track now. Probably now he would have survived. Sorry, what was your question? You said what you said? Yeah, yeah. He was a Pitt Meadows grad, as a matter of fact. If you play sports where you strike something like a ball, tennis, baseball, soccer, golf, hockey, you're often told to follow through as you make contact. How would following through help the ball leave with a greater velocity? How would it change your momentum more than not following through? Which of these two variables are you changing, Carson, by following through? So you've lifted weights, you've maximized the force. What's the other variable you can change? Time. If you can make the time of contact even a little bit longer, that's more impulse that will get transmitted to the ball. It's going to leave faster. So as T increases, impulse increases, so V final increases. Anybody here play tennis? Okay. To do a drop shot, you actually pull back right at impact. You want the time to be near zero, and if you do it just right, you can just drop the ball straight down. Anybody here play baseball? When you bunt, what do? You're pulling back right at impact. You want to minimize the time. You want to deliver almost no force to the baseball, just enough to bring it to a stop. The best bunt, if you can drop it straight down and have it trickle just about a meter in front of you, that's like perfection. Can you put the test face down in the appropriate block and then head to your class? Thank you, kiddo. Okay. What has more momentum, a 1,000 kilogram car moving at 100 kilometers per hour or a 2,000 kilogram truck moving at 50 kilometers per hour? Your hint is it's a what? They're the same. I was going to say it's a trick question. They're the same. What that means, Carson, is, Ben, it's called an attention span. I need you here. What that means is if they had a head-on collision, they would both come to a stop because their momentums would cancel each other out. Does that mean they'd both experience the same damage? No. They'd both experience the same force. F equals what? The truck has bigger mass, smaller acceleration. The car, smaller mass, bigger acceleration. That's why in a smaller vehicle, the occupants will often experience more damage. Same force, same impulse. So you can write for number 6. It's the same. Carson, good. My last class couldn't see that at all. Come on. Oh, wait. It's going to be on the line. Does a moving object have momentum? What was our equation for momentum, Ben? You found it earlier. Does a moving object have mass? Does a moving object have velocity? So does a moving object have momentum? Yes, I agree. Follow-up question. Turn the page. Does a moving object have impulse? What did we say impulse was from the very beginning of the lesson? It's not momentum. What is it? Okay, so a moving object will only have impulse if it's changing momentum. And since momentum is mass times velocity, we'd say this: only if v is changing. Or what's a fancy word for a changing velocity? Starts with letter A. Yeah, only if there's an acceleration. If you have an unbalanced force, you have an impulse. Okay. If any of you watch Star Trek, if you're Star Trek fans, they talk about impulse engines. That's the correct usage. They're changing the momentum of the Starship Enterprise. Are they changing its mass? No, they're changing its velocity. The impulse engines make the Enterprise speed up or slow down. When you jump from your lab table to the ground, why do you bend your knees as you land? Why don't you want to land stiff-legged? Yeah. In fact, if you ever see a little toddler who's just learned to walk, like they're 2.5 or they're 3, you'll often see when they come to a curb in the road, they like to jump down because for them, that's still a big height. And watch, they land stiff-legged their first few times, kind of awkwardly. They're learning then. It hurts. And then suddenly you see them when they're 4 or 5 at a playground. Now they're landing, they're bending their knees. Sometimes they're even rolling as they land. They've learned, yeah, what are we increasing? Time increases, force decreases. And since F equals what? ma, your mass doesn't increase, acceleration decreases, and acceleration is what does damage. So you figure this out yourself. And again, it's Captain Obvious physics, but I've told you, Jaden, I like showing you the physics behind obvious stuff that you figured out as well. Here's the why. I kind of like that. Hey, what's more likely to knock out a boxer? Taking a punch while leaning back or taking a punch while coming in? Why? Why would there be more? Would there be more force? Less time. Same impulse because the glove's going to come to a stop. So the glove's going to give all of its momentum to the person's face. It's the same change momentum, the same impulse over less time. So yeah, time decreases. I agree with you then, Jaden. Force increases. Same impulse. Watch a professional boxer sometime. It's amazing how good they are. The punch will be coming in, and you're going to swear they're going to take it, and they barely get grazed. They manage to do that. Or if you watch a heavyweight fight where there's a spectacular knockout, watch some of the old classics, you'll often hear the announcer say during the knockout punch, oh, he caught him coming in. That's what you don't want to have happen. Then it's lights out. Okay? What's your homework? Every question. You've got, I was hoping to give you 20 minutes. You're going to have 16 minutes. I think if you hustle, you can get all of these and the homework from lesson 1 done pretty easy. Let me hit pause